Okay, so here's problem 3 in homework 3 in ME370 in fall 2021. And we have what appears to be a problem in Shigley, but I changed it. I put the forces in different locations. But we have this steel shaft that has these gears on it, and it's kind of a problem. It's sort of overhung. You can kind of see that this gear B, is kind of cantilevered off to the side. And it's transmitting 100 kilowatts at 600 RPM, at a constant 600 RPM, I should say. And we want to determine the location and value of the absolute maximum shear stress in the shaft via principal stress calculations. And we want to draw a completely labeled 3D Moore circle, and we can ignore transverse shear, and here are all the parameters. The shaft is 50 millimeters diameter, or 2 inches, that's about. The big gear is 450 millimeters in diameter. The small gear is 250, and this dimension here, A, is 400 millimeters. This dimension B is 250. Oh, look, there's a little number that kind of like stuck out from there. He's kind of hiding in there. Didn't you see him before? And then C is 150. So it's over. This thing's overhanging 250. So, boom. Here we go. I've written mine out with all of these givens and tried to be, kind of careful, but still kind of I left a spot out there. Look at that. I kind of cheated in there. Look. Now that I'm looking at this, I'm going, boy, must have been made late at night or something. No, I was tired. All right, so let's start with the problem. I start with my geometry. All right, so I don't need the area, so I only got the moment of inertia of the shaft, and just 2 times that to get the polar moment of inertia. I want to get my loads. I use an equation out of the book that gives us, in terms of watts and RPM, will give us torque in Newton meters, and that's in chapter 3. You'll find it. It's a good one to mark in your book because it's often have to look it up. The conversion of combination of getting power from torque and shaft speed is a good one to get. So anyway, I found out that I have 1,592 Newton meters. So we go ahead on this one, do a free body diagram, and we noteworthy that we show the thing is coming down here from that direction, but it'd be better to have it in tangential and radial coming down. So right there, I have it as in tangential and radial, but I labeled them as, that looks like a 2, doesn't it? It's supposed to be a Z. Here, I'm going to put a little thing on it. Still looks like a 2. That's terrible. I already scanned this, so I don't think it matters that I'm going to fix it. I'm not going to rescan it just for that. But anyway, we have I'm cutting this thing apart for this free body diagram. I'm like lopping it off right here, and I'm only looking at that portion so that I could see the torque that's on the inside of the shaft. So I know that torque, so that allows me to be able to find this force right here, and because we have the 1/2 of the diameter of the big gear, and I get 7,074 newtons. And then I can find what the radial part of it is just by taking and multiplying that by the tangent of this, because tangents rise over run, so we're multiplying it by the run, so we get the rise, right? So that's what we get there. So we get 2,575. And then I can do it again, but this time I'm going to look down the length of the shaft, and I'm going to look at both gears. So it's no longer have I cut the shaft, so the torque disappears because now the torque is internal. But now I'm able to find out what FBZ is going to be. And I kind of crammed it over in here, unfortunately. But here's the one that we know, we just found out, and here's the one we want to know. And we get that we have our FBZ, so this at B in the Z direction is going to be 12,733 Newton meters. And then we get the radial one by, once again, multiplying it by the tangent of the pressure angle. And so here we go in the Y direction. Now we want to do our shear moment diagram with the free body diagrams on top of it. Voila. I know, I just kind of like threw it up all there at once, right? So we might want to carefully go through this and kind of see that we agree with all of it. You know, okay, in the XY plane, this is going down and this is coming up. And remember, there's the support at the bearing, right? The bearings were right here. So we see the vertical component of this, and we see the vertical component of that. All right, and then over here, we have the same dealio, right? We're going to see the Z component of that right there. We have the Z component of this coming in that direction. When doing the statics for this, you know, it's a little difficult to decide when you're starting out here which one, if these are both going to be in the same direction. This one, I went ahead and guessed that it was going to be the opposite of the one that was near it. I guess that this one is going to be opposite the one that is near it. And then I do the sum of the moments, and I confirmed this first one right here. Let's see, we'll move this guy up a little bit. I confirmed this first one was positive, so I got the way, and then I did the second one down here. I'm like, yep. All right, so both of these directions I chose for these were correct. But it was a little bit of a challenge right there. You got to be careful with your signs, right? Because you can mess the thing up. It's not completely obvious. It's one reason why I picked this problem. It's going to kind of like expose whether you're able to do the FBD and get the reactions process. Because this one's even more difficult. I decided to make, like in a similar way, that this reaction was going to be the opposite of this, and this reaction was going to be the opposite of that. And it turns out I was wrong. I call this one like the teeter-totter one, right? So like if you push enough of a force with enough of a distance away from the thing, the other side has to like kind of like be pulling down onto it. So I don't know if that's a good explanation, but that's the way I think of it, that when this kind of occurs, right? So during the sum of the moments, about this point, sure enough, this guy was confirmed in a pretty large number. But then you do the sum of the forces in the Z direction, and you end up finding that this actually should be negative, right? So this right here, as drawn, is in the positive Z direction, but it actually, I've assumed it wrong. I end up getting a negative value, so it is actually coming up in that direction. And then I do the shear from those reactions. I can now get the shear for these, right? And it's a left to right thing, and finding this reaction force, which is 2060. We come over here, and then this force comes down and it's going negative, so there's a little bit left over, so there's a negative 515. And then this one's going to put an additional 4,120, so that it ends up coming down to 4,635, which is what this is equal to, so it should come back to 0 at the end of this overhung edge. And then finding the moment of this area, that's just this value times 0.4, remember, because we want to be in Newton meters, right? So this is in newtons, these are in millimeters, so I need to make sure that I adjust for that. But here's the moment that I get right there. The same thing for this right here, right? I can either do two different ways. I could take that 4,635 and multiply it by 0.15, or what I did was take the negative 515 times 0.25 and add it to my 824, right? So that's going to drop it down to that 695.3. Then over to here, we have, once again, I went ahead and left my diagram here because I did my calculations using this thing, but I made a note next to it that this was the wrong way because it's actually coming that way, which is a negative direction. So this is the result that I found, that negative 217.6. And then this 7,074 is coming upwards, so upwards, it's going into the negative Z direction, so it combines, so it's got even larger. And then this reaction is like 20,000, right? So this is not to scale, but it goes down to 12,733, which is what this is right here. It comes back up to 0, so we're good. And then we get the moments. We just got this little tiny area times the 0.4. It's like negative 87.04. And then This is also a negative area, so we're going to combine that. And so I'm multiplying that, 7,294 times 0.25, and then including this with it, I get that 1,910. So that's the answer. Or we could go 12,733 and multiply it by 0.15, and that should get us the same result, because this needs to go back down to 0 where the gears are hanging over. So we want to make sure that we get the moments at the same points, so that this point right here, which is point A, and this point, they combine together, and we get a moment of 828.5 Newton meters. At point C, we do the same thing with this and this, and we get 2,033 Newton meters, and that's obviously the maximum. So now we get to go with the stresses, right? So we have MC over I, we have the 2,033. The shaft diameter was 50 millimeters, so we go 0.05 divided by 2. And here's the moment of inertia, and we get 165.6 megapascals. It'll be on tension on one side and compression on the other, so we'll just keep it as just look at the tension side. And then we have the torque, right? So we found early on 1,592. So we get and divided by the polar moment of inertia right there, and multiply it by R. Okay, we get 64.86 megapascals. And there I labeled a little stress element. And then I did another Mohr circle here, where I find my principal stresses, right? So I find the center of this, and in this case, I plotted the points right here. That's on one face, and here's the stress. It's going to be 0 on the other face, right? And 0 on this face, and which is often the case. This is just a uniaxial problem, right? So there's only stress in down one axis. Pressure vessels have have hoop stress that get out in the other, but most other problems don't have stress in two directions. Okay, so we plotted that point, so we find the center of it, and then I use this as the radius. That was convenient because the center is one of the legs, right? This is the leg that we use here, and then we also use this other leg, and we're able to find the radius. And then we know that is the absolute maximum shear, right? That the radius in this case, because we have the big Mohr circle, is the main one that we were working with. So we kind of answered the problem, but I went ahead and looked at the principal stresses anyway. We have 188.0 megapascals, and the other principal stress, or the third principal stress, I should say, the one that comes back over here, is going to be C minus R, right? And that gets a negative 22.4 megapascals, but it's in compression. But the main question was asked was the principal absolute maximum shear, right? Absolute maximum shear stress is this guy at 105 megapascals at bearing C. So I also did an FEA of this one. If you see the other problem one, you saw that I did an FEA there. Let's see, I don't know if I changed anything in this. I can get rid of it now, right? It'll probably ask me to save it. I'll save it. Why not? I don't think there's anything wrong. Okay, so this one, it's a little difficult to model shafts sometimes. The SolidWorks simulation does have this nice bearing boundary condition that we can add onto there. Let me see. So it looks kind of like that right there. So you can see that I have these fixtures as bearings, but you need like a cylindrical face to be able to do it. So I did split lines right there. And I included the gear as part of it. I didn't make them as separate parts. So when we look at stresses, if we were going to look at stresses near the gears, we'd have to look just to the side of the gear, and then we'll talk about stress concentration, where that's going to mess up our answers. But this right here, I'm just trying to demonstrate some things, and I thought this was a good one to do. So let's see, I'll show the stresses, and the stress that I'm actually showing right now I had left on. It was the last one I looked at. Something called, I was just looking to see what would happen with it, but I'll put it back to von Mises. That's just a good value to use. And So here's the stresses. So you can see where it's stressing, like right there and right there. But there's the thing that messed up with the bearing is that there should be stress in between there. So I'm not quite sure how I would go about fixing that. One thing I would mention, it's a good visualization tool here, is that I have it turned on so that it's a ghost of what the original undeformed place looked like. So you can kind of see what this thing is doing. And you can see that being cantilevered over here really, and this is an exaggerate, this is like 54.8 times the amount of deformation that actually exists, right? You wouldn't even be able to see the deformation in the real thing. Like I can go to settings. Is it settings or is it display? I think it's definition right here. And you go like the true scale, right? So here's the actual one. And there's got this little thing that almost like a little, I don't know even what you might call it. You can barely see any, you don't really see deflection. It's just too small in reality. But I think it does nice to have that exaggeration so you can kind of like see, similar to what we did with the pool noodle, right? To try to demonstrate where this thing is coming out of plane, right? That it's going up and over here. And then this one also, so that the shaft is bending in two separate ways. If we go and just take a look, and I'll just probe in a spot nearby this right here, and we'll just look at the values are even without knowing. I get 175.3. I got 187. There's a bunch. There's a bunch of nodes here. I could just pick off the thing. Here's a 127. But you can see these little red spots. I get kind of an idea of that I'm in the range. There is a principal stress 1 that we can look through here. Principal stress 1. Let's go to this. So the first principal stress, I should say. All right. So that changed it a little bit, but when I was probing it before. I got, here's a really large one, 238.5. Oof. All right, there's a 136.2. I also did this other thing, which is useful. List selected, and I grabbed a hold of this ring right here, this edge, and you can plot the stress that's around there, right? So it just grabbed all of the nodes that are on this split line right there. And it showed you what the stress values were, and you could see that we're coming up to like 185, like right in there. Remember, our principal stress answer was 188, was our largest principal stress. So we're kind of in the range. Once again, there should be stress in between there where that bearing is. So I'm not sure what to make of that. And I tried to use the make it so that it was only at a circle, and it says that you can do that, but it wouldn't let me use that as the boundary condition. And then look at this one right here, we get like 192. So we know we're kind of in the right range, right? We didn't do anything too crazy wrong. I think, the point of using the FEA at this stage in the semester is to see you kind of like give you the picture of the visualizing these stresses, but also see that we can calculate something by hand and get it to match the computer. But here's an instance where this boundary condition isn't a believable thing, right? It's not behaving like it's you know that it would have to. So that's like one of the limitations of modeling, is you're kind of stuck with situations that don't like lend themselves perfectly to the modeling constraints, right? The model wants the people who created the modeler thought up like, okay, well, this would be a useful feature and this would be a useful feature, but inevitably your feature, if you're cynical, the thing that you want done doesn't really match up with the features that they created. So anyway, video's too long. Once again, another 19 minutes, but I had this added bonus stuff on the end that I don't know if anybody's going to listen to or watch, but if you did, you tell me about it. Let me know. Thank you.